Conventional quantum computers lose their data if a single atom encounters stray thermal energy. Topological quantum computation solves this vulnerability by storing information globally across space, rather than in isolated local particles. This physical protection requires restricting electron movement to a two-dimensional plane. In 3 dimensions, exchanging two identical particles twice returns the system exactly to its starting state, limiting nature to bosons and fermions. Confining particles to 2 dimensions changes the mathematics of exchange. Swapping two identical particles can multiply the wave function by any complex phase factor, creating a third class of matter called anyons.
Abelian anyons merely alter the phase factor of a state. Non-Abelian anyons modify the state matrix itself, meaning the precise sequence of particle swaps changes the final outcome of the physical system. Tracking non-Abelian anyons over time generates trajectories in 2 dimensions of space plus 1 dimension of time. These continuous lines twist around each other, forming geometric structures known as braids. Each physical crossing of anyon paths performs a precise mathematical operation. The resulting braid acts as a quantum logic gate, transforming the underlying qubit state through pure geometry rather than localized forces. Local noise cannot undo a braid. Stray electromagnetic fields might jiggle an anyon, but unless the perturbation forces the particle to loop completely around another, the encoded quantum information remains completely uncorrupted. Non-Abelian anyons form a manifold of multiple states with identical lowest energy. The quantum information is distributed within this degenerate ground space, hidden from local interactions with the environment. Engineers realize anyons by subjecting semiconductor layers to temperatures near absolute zero and intense magnetic fields. This environment triggers the fractional quantum Hall effect, where electrons break into collective fractional charges.
Another pathway uses topological superconductors to trap Majorana zero modes at wire boundaries. These modes are physical implementations of icing anyons, acting as half an electron split across distinct spatial coordinates. The computation sequence starts by injecting energy into the system to pull anyon pairs out of the vacuum. This process initializes the qubits into a known, highly stable starting state. Voltage gates systematically alter the local potential wells containing the anyons. By dragging the particles around one another in precise trajectories, the system executes the pre-planned braid pattern. To read out the result, pairs of anyons are brought back together in a process called fusion. The particles either annihilate each other or combine into a detectable standard particle.
Observing the fusion channel reveals whether the pair combined into a vacuum state or a fermion state. This binary physical outcome corresponds directly to reading a 0 or 1 from the qubit. Ising anyons cannot perform every possible quantum calculation on their own. Braiding them only yields a subset of logic gates, requiring supplementary non-topological operations to achieve universal computing capabilities. Fibonacci anyons solve this limitation completely. Braiding these specific particles allows the execution of any quantum algorithm using purely topological moves, bypassing the need for error-prone non-topological interventions.
Standard quantum computers require thousands of physical qubits to correct for errors in a single logical qubit. Topological hardware eliminates this massive overhead because the hardware itself prevents errors from occurring. Modern layouts construct semiconductor nanowires coated with superconducting shells. These networks form junctions where anyons can be mechanically routed and swapped without colliding or losing their quantum identity. Scaling these physical systems involves integrating millions of anyonic junctions onto a single chip. This architecture shifts the challenge of quantum computing from active error correction to precise material engineering. Every swap of non-Abelian anyons corresponds to a unitary matrix multiplying the vector representing the ground state. Because matrix multiplication is non-commutative, the order of the swaps determines the ultimate calculation outcome.
anions carry fractional electric charges that are impossible for isolated electrons to possess. These charges emerge as collective excitations, acting as localized whirlpools within the dense fluid of interacting electrons. Mathematicians classify anion trajectories using homotopy classes. Two paths are topologically equivalent if one can be continuously deformed into the other without cutting through another particle world line.
While topological protection stops phase and flip errors, systems face leakage errors, where anions transition into unauthorized states outside the computational space. Designers use tight potential wells to minimize this leakage. The entanglement in a topological system is non-local. Information resides in the global topology of the shared wave function, making it completely invisible to local measurement probes. Fractional quantum Hall systems exhibit chiral edge modes, where currents flow in only one direction along the boundary. These paths guide anions securely, preventing backscattering from defects in the material. Physicists verify the presence of non-Abelian anions using electronic interferometers. Splitting an electron beam around a trapped anion creates interference patterns that depend strictly on the topological charge inside.
The algebraic structure underlying topological computing is the Artin-Braid group. The generators of this group satisfy specific relations that dictate how multi-particle swaps combine and simplify mathematically. In topological superconductors, the pairing of electrons into Cooper pairs creates a macroscopic quantum phase. The Majorana zero modes emerge precisely where this phase undergoes a localized topological defect. To execute arbitrary quantum gates with Fibonacci anions, algorithms compile sequences of hundreds of individual braids. This geometric approximation can achieve any desired level of precision by increasing the braid length. Although anions require low temperatures to form, their topological states are protected by an energy gap. Thermal fluctuations lower than this gap cannot create stray excitations to disrupt the computation.
An alternative approach simulates anions on a two-dimensional spin lattice using the toric code. Here, localized magnetic defects behave like anionic particles that can be actively braided via software controls. Multi-anion states are tracked using fusion trees, diagrammatic structures showing how multiple particles sequentially combine. The branches of these trees map directly to the basis vectors of the quantum system. The mathematical verification of fault tolerance relies on deep topological invariants like Tureyev-Viro tensors. These tools prove that the computational space remains robust against continuous geometric deformations of the substrate.
Operating these chips requires dense cryogenic control interfaces. High-speed classical electronics route voltage pulses to anion junctions at millikelvin temperatures without introducing heat leaks that could collapse the phases. Realizing topological quantum computing removes the primary bottleneck of physical error correction. By embedding logical gates directly into the topology of spacetime, computation achieves the scalability required for complex molecular simulation.